All right. So, welcome back. Everybody's super excited about chemistry. I can tell all the chatter. Very excited. So what we're going to do is we're just going to introduce some reactions. Strong base, strong acid, weak base reactions. And then use our knowledge of Kas, Kbs to predict equilibrium concentrations. So we're going to use acid bases with ice charts to figure out new concentrations. Alright, so let's first just talk about how do we predict reactions. So an acid-base reaction, right, means I have either a strong acid or a strong base in the solution. They could be reacting with each other, or I could just have one in water or the other one in water. So we looked at strong acids before, right? There's 6 of them. I'll pick. Right, so that's my strong acid reacting with water. What would be then one of the products of the reaction? Those are the 2 of them, H3O+. What do I call H3O+? The hydronium ion. And if it's a strong acid, which direction does this proceed? Mostly. Mostly to products, right? Right, that'd be more accurate. It doesn't really equilibrium in the same kind of way. It really just makes products. Or I could have a strong base, right? If it's now a strong base, how is the water acting in this case then? Acting as an acid. So what should one of the products be that we make? Alright, strong base. It's tricky with the sodium in here. Makes things a little quirky. It's a little weird. Bases are a little trickier in that you're going to make this hydroxide in solution, and the water doesn't really change like it does with the acid. Alright, what if I now had these 2 things react with each other? I have a strong acid reacting with a strong base. What if I chose to do this? Again, this is really different this way. Alright, so now I have a strong acid reacting with a strong base. They both completely dissociate, right? Because they're strong. They both completely dissociate. So what should one of the 2 products be that gets made? Let's do it this way. What are the 4 ions they're going to break up into? What is one of the ions I should have on this side? I should have an H+. I should have what else? A Cl-, an Na+, and an OH-. Okay. What 2 products am I now going to make that are different from what I started with? One's going to be a water, and then the other one's going to be a salt. Have you guys done this in lab yet? Reacted these things together? Not yet. So every time you have a strong acid with strong base, you make water and a salt. Let's do one more of these and then we'll look at some other things. What if I had what's this one? I don't remember that one yet. Nitric acid, potassium hydroxide. These are both on your strong list. So what must be one of the products? Water. So then what salt is left over? Potassium nitrate. I drew them as equilibriums, but what really should the arrow be going? Towards products or towards reactants? Really, it's really just towards products. What K value would it have to tell you that's just linked towards products? Well, like greater than or less than. Definitely greater than 1. All of these K reactions will have a K much, much, much greater than 1. They're going towards products. Alright, so that's a little bit of review. Let's now look to see what happens when you have weak acids and weak bases. I realize this is a typo. It should say weak acid, weak bases. That's what I meant. Alright, so weak acids and weak bases. Alright, so let's say I have which acid is that one? Not one of your 6 strongs. Acetic acid, my go-to, all-the-time favorite, acetic acid. Pretty much every example will be acetic acid. It's just great. Vinegar, smells strong. Just, I like it. Alright, so now this is a weak acid. So does it make water in the salt? No. It makes, right, our hydronium, and then leaves this ion by itself. Do I have the arrows drawn correctly that there are going to be some back and forth? If it is a weak acid. Because it's weak, it's not going to make all products. Some of it's going to stay like it is. And some is going to go over here. But some is just going to stay over here. So finding the pH of a weak acid solution, right, where pH is that, is not going to be as straightforward as it was if it was just a strong acid. We have to use an ice chart. Alright, so before, we didn't have really the same kind of equilibrium, right? It was K greater than 1, only going one direction. Now, I have a K less than 1, which means I need to use an ice chart in order to figure out these equilibrium concentrations of everything. And it would be the same if it was a weak base. Let's do this one. Same thing. So now I have a weak base, which definitely makes some ammonium and some hydroxide. But it doesn't all completely convert to hydroxide. So I have to figure out what it is at equilibrium in order to figure out the actual pH of these solutions. So if you don't have a calculator handy, you're going to want to fish it out. I'm also going to switch 2 orders of slides. I'm going to save the one called determining K from pH and do this one first. Determining equilibrium concentrations from pH and Ka. We'll do that one first, then we'll come back to this one. Alright, so I now have a weak acid, generic HA, and I know lots of things about it, right? I have my generic acid, that I have made a solution of, that I know its concentration, and I know it's Ka, but I want to figure out what happens when it gets to equilibrium. What are the concentrations of all of the species in solution? So, first thing, ice chart. In order to write an ice chart, what do I first have to have at the top of the ice chart? I need to have a chemical equation, right? Otherwise, there's no chart. Title list, it's crazy. So I have my weak acid. If it's a weak acid solution, what does that mean the other reactant is? Water, right? It doesn't tell you anything other than it's a solution, which must mean it's just in water, just dissolving. So if HA is the acid, what should one of the products be? Yep, A minus, right, because it donates a proton. Water has received that proton, so what is the other product? This guy, right? That's how you know it's an acid reaction. It should make some acid. Sounds crazy? Not like drugs acid. Like it makes like a hydronium. That's what it makes. It makes acid. Alright, so now we're ready for an ice chart. Alright, so we have this. Down the side, right? Let's fill in the things we know about this. They gave us an initial concentration of HA, so you can plug that in. What do I do about water? Does water's concentration change over the process of reaction? It doesn't. I usually just draw an arrow straight down saying it's important, don't leave it out, but it's not going to change. You can do little dashes. I think mastering likes little dashes in each one, whatever you want. It's fun. The instant I start the reaction, is there any concentration of these two? No, we assume those to be pretty much zero. Alright, so now I'm ready for the change. Again, no, I'm not ready for the change. What should be, how many X's should I subtract off of HA? 1, right? 1X. How many A minuses should I then make? +1 and +1. Now this is going to be 0.04. Ooh, my marker's dead. 0.040 minus X plus X and plus X. Alright, so is this a Ka or a Kb? Ka, 1, they gave it to you. 2, it's an acid, alright, so Ka. That equals, what should I put in my numerator? X squared. What goes in the denominator? Right, the product, yeah, there we go. 140 minus X. That equals 4.0 times 10 to the negative 9th. If you were going to solve this out regularly, what would you then have to use? It's a quadratic. We're not going to do that. We're going to make an assumption and see if our assumption is good. Okay. So you're right. I would have to do a quadratic because it's squared on top, but it's not squared on the bottom. But let's take a side note over here. If I have a weak acid, what does that tell me about how much A minus and hydroniums are going to be made? A lot or not a lot? Not a lot. Would you say that they are going to be the smaller value? Probably. I would say that, yes. Right? So I'm starting off with this. And it's going to make some of these, but since it doesn't completely ionize, since weak acids do not completely, maybe there's another E in there, ionize, we can assume if they don't completely ionize, what has happened to the concentration of HA? Hasn't really changed. So what assumption can I make about this statement right here, that I can ignore the minus x. That the concentration of the weak acid has not changed during the experiment. We will have to double check our math to make sure there's a good assumption. It is good most of the time. There'll be some times when it's not a good assumption. So, what has happened to my Ka equation if I no longer have this minus x? I now have x squared over 0.040 equals, how do I solve that? Pretty straightforward, right? I just multiply by that square root. Done. Much faster. So I'd have x squared equals, what's that, 1.6. What units does x have? Molarity. Alright, that's pretty easy. The question is, was that a good assumption? So the question is, we made this assumption that the minus x was very small compared to the actual value. We're going to use what's called the 5% rule. So we're going to check this assumption. What's called the 5% rule. And it's really because experimentally we only know Ka, the thing I'm comparing this number right here. I only know Ka plus or minus 5%. It's temperature dependent, it's dependent on a few other things, the ionic strength of the solution, a bunch of things go into it that we take analytical, we'll certainly take into consideration. But really our Ka values are like, plus or minus 5%. So this assumption, if I'm within that 5%, then we're good. So what we need to do is compare what we got to 0.04 and see if it's less than 5%. So the 5% rule says you take the value that you get for x, divide by initial concentration times 100%. If that is less than 5%, good assumption. Alright, so we got this value for x. If I remember correctly, this number is way less than 5%. .03%. Is this a reasonable assumption then that the concentration did not change? Very good assumption. I mean, you can even look at it. My original concentration was 0.04. This is 0.00001. So almost nothing compared to the original. Alright, so good assumption. Now we need to finish answering the question, which is, where did my question go? The equilibrium concentrations of HA, A minus, H3O plus. So, X is which of these, more than one of these values? Right, it's A minus in the hydronium, and then HA is still just 0.04. What if I wanted to know the pH? Final question, what's the pH of this new solution? How would I figure out that? If the follow-up question is, what is the pH at equilibrium? We just said X is the hydronium, which equals, at 1.23 times 10 to the negative fifth. So what is pH in math words? Negative log. So that should be where ballpark that? It is a weak acid. Like hydrochloric acid's pH is 0.08, really close to 0. So a weak acid is going to be in the 3 to 6 range. The closer to 7, the even weaker acid it is. I don't think there's any real weak acids. There probably is. It has a pH between 6 and 7. It's usually a combination of things in your solution at that point. Then you're into the base side. Closer to 14. Closer to 14, the stronger the base, because it means it's all hydronium. Zero hydronium is all hydroxide at 14. How about we do another one? Chris. Yes. If you get a pH less than 1 and you know it's a weak acid, your math has led you astray. Yeah. So that's a good rule of thumb. If you get a pH way low, but you know it's a weak acid, then somewhere you have done something crazy. All right. How about we do another one? How about we do? What do I got? All right, let's see here. What blank piece of paper do I still have left? Okay. All right, let's try. Alright, so I have a 2.5 molar nitrate acid solution. It has a Ka of 4.6 to the negative fourth. Even if you didn't know if this is a strong or weak acid, what's some giveaways that's definitely on the weak side? Its Ka is less than 1, so definitely weak. Okay, so even if you weren't sure, if you didn't have that list of 6 strong acids in your head, you're like, less than 1. So I need to set this up like a weak acid reaction. Alright, so if I have what must be the other reactant, if I didn't tell you anything about it? It's going to be water. If it's a weak acid, what must be one of the products? Yeah, hydronium. And then you have that left over. It seems like I keep repeating the same thing over and over and over again. Is because we're going to get to the point that we're going to have to predict new products. So just getting to the habit of seeing this, predicting that, and then setting up your table. Because it won't always be plus water. It'll be plus something else. And then we'll do some other things with it. Alright, so setting up our ice chart. Alright, so I told you the initial concentration of this. What do I do about that water? Yep, just placeholder. Do I initially have any of these two? No, we assume 0. Alright, how many X's does the acid lose? 1, it loses 1. And how many does my hydronium gain? And how about my ion? Also 1. Alright, so now x squared over 2.50 minus x equals 4.6 times 10 to the negative 4th. Alright, so which x do I assume to be small? The x's on the top or on the bottom? These. I want these to be small. Because if it's on the top, then it's 1 and then it's funky. So we assume that this x down here is small. We're going to call it 0, right? That way it's 2.5 minus 0. But that doesn't change the x's on top. Like, you don't make the assumption that all x's are 0. Otherwise your calculator freaks out with a 0 divided by 2.5. Real angry. It'll probably yell at you and say error. Or syntax error, or something like that. Alright, so then we solve for x. So what units does x have? Molarity. Alright, oh, Christopher. It's the Ka. Yep. Alright, so how do I go about checking if this is less than 5%? What number do I put on the top of the fraction for the 5%? Yep, I put the x on top. Compared to the original solution. Did we make a good assumption saying that x was pretty much 0? We did. Good assumption. Alright. Now we're ready to answer the final question, which is actually the only question. How do I figure out pH now from all the stuff that's on my thing? There's numbers everywhere. Which one do I use to find pH? The x. So this is going to be the tricky part about doing these problems. You're going to see there's just numbers everywhere. And try to keep your work organized so you can figure out where the heck did I put that number at. This pH is pretty low. What makes it so low, do you think? Compared to the last problem, What's the biggest difference between these two weak acids? The original concentration, right? The last concentration was 0.04. This is 2.5 molar. Way more concentration. You expect a more concentration. It's going to give off more hydronium. So even though it's Ka is less than 1, there's more of them. But I'm on the right side of 7, so that's excellent. You guys want to do one more easy one, or do... Oh, question first. Yes, you would then have to go back and do the quadratic equation. Sure. If you would love to do the quadratic, I'm not going to argue against doing the quadratic. More likely you're going to make an error. But you're more than welcome to do it the long way. Yes. Yep. That is correct. Alright, so you want to do one more easy one, or you want to do the challenge problem? Okay. Let me figure out where I put it in my notes. Yes. Ask away. No, you can't use the graphic calculator. You can certainly use the quadratic equation, but you have to do it by hand. Here it is. You're going to want more space than this. Much more space than that. Alright, so again, another fun conversation starter with your roommates tonight. Turns out codeine is a weak base, above and beyond it being a powerful and addictive painkiller. It's a weak base, which means it has a K, A or B, it's the base. Has a KB, but I didn't give you the KB. I gave you lots of other information. So it's going to be 3 parts. First, we have to figure out what is its reaction. I gave you the Ka, so you have to figure out the Kb. And in the end, I want to find the pH of a codeine solution. It looks like cod. It's not really fish. It's not fish in water. Although if you watch Saturday Night Live, it's like the Fish-O-Matic. Yeah. That one gets me every time. It's funny. Alright. Alright, first thing, we want to figure out what is the reaction of codeine and water. Alright, if this is the weak base, what's water acting as? Acting as an acid, right? So if it's acting like an acid, is the water going to take on a proton or give away a proton? It's going to give away, so what has to be one of the products? OH minus. If it's given away a proton, who has taken a proton? The codeine. I'm going to just call it HCOD, indicating that it has an extra proton that doesn't normally have. Okay. Oh, yep. Alright, I know the Ka of the protonated codeine. Why can't I use the Ka? What's going in? The base, right? So I have to write it as a Kb. Otherwise, I have to change around the whole, because I'm going to give you a solution of this. And so we have to know it as a Kb because base is going in and making base products. Alright, making OH minuses. So if I know the Ka is equal to 1.2 times 10 to the negative 8, I would say there's 2 different ways you could do this. Both are fine. What is the one thing that Kas and Kbs are related to? Kw. So I would set up that relationship. You certainly could figure out this. I didn't give you the P's for any of those, so I would just use this one, the P-free version. P-free, P-less, without P. Alright, what's KW equal to? I'm going to give it to you on the test, but you, at this point, probably have it memorized. This, yes. Close. They add up to 14, so it could be 7. Alright, so then I know this. So then what should that be? 1.00, 14. What was that? I always give you the KW, but, and the KA was given in the problem. So I got my KB to equal to, everybody else get that? Anyone else playing along in the audience? Okay. Alright, so we are now ready to actually start the problem. So that's all just setting us up to be able to solve it. Alright, so now I'm going to rewrite my equation. You could certainly, if you had left yourself space, you could put the chart right there. Alright, so they gave us the initial concentration in the base. What do I do about this waters? Yep, just big old. What do I assume to be true about the concentration of these guys? Right, that they start off at 0. It's not a bad assumption, right? I mean, reality, right? If I have water, I definitely have some hydroxide. They have to be in there. We're going to assume that they're very small compared to the other things I'm going to do to it. Because it's a weak base. It's a weak base. It's not fully right. So if I want pH, I need H3O pluses. I didn't give you anything that makes an H3O plus. So you have to make an ice chart to figure out what this new concentration is. Yeah. So that's why it makes it a challenge problem, right? Because I want pH, but we're going to make OH minuses. And it's come around the end, figure out what pH is. Alright, so how many X's does a codeine lose? 1, right? And these guys each gain 1. Alright, so now we have our KB, which is up here. I always write it out including the minus X, and then I rewrite it. You could certainly skip that step and just make the assumption, as long as you remember that you made the assumption and to check it. Which in your panic, you may not remember, because you were scooting along these questions. Or excitement. I guess it could be excitement. The excitement to finish, not panic that you're running out of time. Alright, so alright, so if that is your X, I'm going to double check my 5% up here in this little box. Did I make a good assumption? Good. Alright, what does this X tell me about my solution now? Concentration of hydroxides. I want to know the pH. A few different ways you can figure it out. Any suggestions about how I get from hydroxide concentration to pH? Sure, I could find the pOH and then relate that to 14. That's good. Or if this is OH, you could relate it back to KW. That's fine too. They both will work out the same. Alright, because KW is also that's also true about KW. So you could plug this into that, knowing this, find hydronium, and then find pH. I think they're about the same number of steps. I think on my notes I did this one. That'll be fine, or you could do it the other way. You get the same answer either way. They're about the same number of steps. Is this... Oh, question first. This one? Or this one? Mm-hmm. Because pK is 14, right? Because Ka is 1 times 10 to the negative 14th. The negative, that they out is 14. Oh. This one? The other way. There we go. Oh, that shouldn't be a. That should be a W. Sorry. That should be a W. Does this pH make sense with what you put into the solution? Yes, right? Because you put a base in. Is this a basic pH? Right? It's like medium of the road pH for a base. Right? 9.5-ish. Right? 7's neutral. 14's way basic. 9. That should make scientific sense. Questions about that? Mm-hmm. Yeah. Oh, if my X, yes, yep. If somehow we end up with an equation where it's a 2x, you would put the 2x up there. Chris? Nope. One or the other. Yep. And they should come out the exact same. So, I really like things at the 14. That's my thing. But if you prefer this one, that's fine. They come out the exact same. You're going to find one you like better than the other. Let's see. Other questions about this problem? Yeah, Kelly. The solution. The only way you know that is by writing out your balanced chemical equation, and your X is OH minuses. So the only way to get the pH, which is specifically H3O pluses, is to find the concentration of this and then relate it to 14. Right, so in this case, I have a base, which can only make hydroxides, but I want to know pH, not pOH. So if I had taken the log of this, which I did, right, the 4 is the pOH, which, if you, for some reason, got yourself turned around, hopefully your scientific intuition clicks on at that point and like, wait a minute, this is a basic solution. I can't have a pH of 4. I bet I just found the pOH. Hopefully while you're working these, I'm working on it so your scientific intuition should hopefully lead you in the correct answer. So if you get an answer of 4 and you're like, wait, this is supposed to be basic. 4 is definitely not basic. And then you're like, oh crap, that's pOH. And you're good. Since you guys look so blown away by that, I'm going to stop there, and we'll do what if I gave you all the concentrations but you didn't know the big K? We'll do it in reverse. Hopefully that was exciting for everybody else. Man, I love these problems.